Next, let's look at a few simple examples of summations that we can express in closed form. So instead of expressing it as a sum of a bunch of different terms, we can take those bunch of different terms and express it in a single simple formula that can be evaluated in a few steps as opposed to 1,000 or 10,000 steps or however many terms you have. Now, it might seem like there's, since there's our examples, that you should be able to do any number of summation problems like this, but there's really only a few that you can really solve practically. So the tricks that we use are special tricks that were invented for particular problems, and you might see slightly similar tricks. There's very a small range of things you can do with these summations and writing a summation in closed form. Most of the time you're out of luck in terms of trying to write this in a closed form with just a few simple terms. But we'll discuss a few examples where you can write a summation in a simple closed form, and we'll show you how to do that. So there's a few rules. So the first one is that the summation I equals 1 to n of 1 is equal to n. Now why is that true? Well, on the left we have the summation I equals 1 to n of 1. Well, by definition, we take this expression and we replace I with 1. Now, since there's no I in the expression, there's nothing to replace, so we just get 1. Next, we add to that the same expression, but with I replaced by 2. Now, since there's no I, when I replace I with 2, I still get 1. So I get 1 plus 1 plus 1 plus all the way up to the nth term. So this is the first term, second term, all the way up to the nth term. So there are basically n of these. And when I add 1 together n times, I just get n. So the sum from 1 to n of 1 is just equal to n. So that's the most simple type of summation you can do. The next example is the sum I equals 1 to n of I is equal to n times n plus 1 over 2. So there's our theorem that we would like to prove. So the left-hand side, recall, is 1 plus 2 plus 3 plus 4 plus ... plus n. So this would be the open form. And then the closed form is just n plus 1 over 2. So this is the closed form because you can compute it in a finite number of terms. Doesn't matter how large n is. If n could be 100, I can multiply 100 times 101 divided by 2, 5,050. And the sum from 1 to 100 is 5,050. So if you add 1 plus 2 plus 3 plus 4 plus 5 all the way up to plus 99 plus 100, you get 5,050. And this formula works with any terminating value n, so it's a handy formula to have. So let's prove this. So the trick here is to give the series a variable name. So let's call the whole thing s. So we're basically trying to find s. So s is equal to 1 plus 2 plus 3 plus all the way up to plus n minus 1 and then plus n. And then the trick is that, well, s is also equal to n plus n minus 1 plus n minus 2 plus all the way down to plus 2 plus 1. So it's just the same set of integers written in the reverse order. So this is a handy trick that was invented by a guy named Carl Friedrich Gauss in the 1700s. And the idea is to write these matching up in reverse order, and we line them up so 1 is matched with n, 2 is matched with n minus 1, 3 is matched with n minus 2, and so forth. N minus 1 is matched with 2, and n is matched with 1. So when we add them, so if I add s plus s, I get 2s, and if I add them the way they're matched, well, n plus 1 is just n plus 1. So this is the first term and the last term. And then I can add to that, but what do we have here? We have n minus 1 plus 2. Well, what's n minus 1 plus 2? Well, it's n plus 1 again. So this is for position 1, for position 2. and so forth. If we say what's n minus 2 plus 3, n minus 2 plus 3 is n plus 1 again, and that's for position 3. And we keep going, and then we have here n minus 1 plus 2, and n minus 1 plus 2 is n plus 1 again, and that was in slot number n minus 1. And then we have n plus 1 for the last one, and that was in slot n. So I have a summation of n plus 1 taken n times. So 2 times the sum is equal to n times n plus 1. So therefore the sum has to equal n plus 1 over 2. Remember, s was just equal to the sum from 1 to n, so therefore the sum from 1 to n has to equal n plus 1 over 2, and there's the formula. So this is a neat little trick that works for this specific example. Another way to prove this formula is using mathematical induction. So you can basically prove that this is true for n is equal to 1, and then second, prove that if it's true for n is equal to k, it must also be true for k plus 1. So that's an alternate way of proving that. And instead of proving this using mathematical induction, I'll prove a slightly more complicated one using mathematical induction. So the next one says that the sum from 1 to n of I squared is given by n plus 1 times 2n plus 1 all divided by 6. So if I do 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49, I just replace n with 7, and that's what I get, whatever is given by this formula. So let's treat this one using mathematical induction and see where it takes us. So the first step of mathematical induction is the basis step, so the basis for induction, and we want to prove the formula is true for n is equal to 1. So we basically assume the statement is true for n is equal to 1. And really what we have here is a sequence of statements. So we have some statements P1, P2, P3, and so forth. And for every value of n, we get a different statement. So if I replace n by 1 in this formula, that's one specific equation that would have to be true. If I replace n by 2 in this formula, that's another equation that has to be true. If I replace n by 3 in this formula, that's a third equation that has to be true, and so forth. So for mathematical induction, we first want to prove that P1 is true, and then we want to prove that if Pk is true, that Pk plus 1 must also be true. So it basically knocks them all over like dominoes, right? Because we prove that the first one's true, then we prove that whenever any of them is true, the one immediately following that's true. So you apply that for k is equal to 1. Well, P1 is true, that implies P2 is true. P2 is true, that implies P3 is true, and so forth, and they all get knocked over. So the basis step, we have to show that the sum from 1 to 1 of I squared is equal to 1 times 1 plus 1 times 2 times 1 plus 1 over 6. Well, the sum of I squared is just going to be 1 squared, and this is going to equal 1 times 2 times 3 over 6, and that checks out. 1 squared is equal to 6 over 6. 1 is equal to 1. So the basis for induction is satisfied. This formula, whatever it does for other values of n, at least it works for n is equal to 1. And usually n is equal to 1 is the easiest one to prove. So we have our basis for induction. Once we have the basis for induction, we have to do our induction step. So now that we have P1 is true, we have to show that step 2, induction step, so we need to show that Pk implies Pk plus 1. So whenever the kth element is true for any integer k, any positive integer k, then k plus 1 is true. So if k is true, k plus 1 is true. So to do this, we always start by assuming that k is true. We don't need it to be true. We're just proving the logical implication, not necessarily the actual validity. So it's possible that they're all false, and yet you can still prove that if pk is true, then pk plus 1 is true. So you're only saying if one of them is true, then the next one is true. So you're proving an implication. So we can start by assuming, so assume that the formula holds for n is equal to k. So if it holds for n is equal to k, that means 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared is equal to k plus 1, 2k plus 1 over 6. So we're assuming that this formula works if we use n is equal to k. We know that's true at least for k is equal to 1, but now we're assuming for any value of k, the formula works. And if it works for that value of k, will it work for k plus 1? So if it's true for one value of n, will it be true for the next value of n? So if it's true for n is equal to k, will it then be true for n is equal to k plus 1? So the easiest thing to do is say, well, okay, how can we get this formula, which we're assuming to be true, to look like the formula for k plus 1? Well, let's add k plus 1 squared to both sides. So assuming that this is true, we can add to both sides plus k plus 1 squared. So that's going to equal k plus 1, 2k plus 1 all over 6, and then times, or plus, k plus 1 squared. So you see, I have the formula for k here and here. And then I added the same thing to both sides. So if the formula for k is true, this formula must be true. Now the left-hand side is just the sum from 1 to k plus 1 of I squared. So this is the formula for, on the left-hand side, for k plus 1. Now we just have to show that this junk on the right-hand side is this formula if you replace n with k plus 1. Okay, so let's see how we can do that. So we have to analyze this right-hand side. So we need a common denominator, so we have k plus 1, 2k plus 1 over 6, and then plus, now k plus 1 squared is going to be k squared plus 2k plus 1, like that. And let's multiply and divide by 6. Right. So we have 6k squared plus 12k plus 6 over 6. And if we combine these, so the whole idea is to combine them and show that all of that's equal to k plus 1, so k replaced with k plus 1, k plus 2 times, so if I replace k with k plus 1, this 2 will factor, so we get 2k plus 2 plus 1, so 2k plus 3 all over 6. So really, you just have to show that this plus this is equal to k plus 1 times k plus 2 times 2k plus 3. And in fact, they are equal to each other. So you can multiply this one out. So this would be the formula for k plus 1. And you can multiply these guys out and just show that they're the same thing. You get the same thing using either this way or that way, and that proves that they're equal. So basically, I'll skip some of the algebraic details, but this essentially shows that if the formula works for k, it also has to work for k plus 1. So this would be another example of mathematical induction.